All right, so what we just talked about is this idea that before you hit the ground, you need to contract your muscle. What that's going to do is that's going to use that muscle contraction and that passive stiffness within your series elastic component, the extracellular matrix of the muscle, as well as the tendon. And now what it's going to do is it's going to tune that stiffness perfectly. And when you tune that stiffness perfectly, the result is you can store and return the most energy possible. All right, and that's really the key component. You guys all know this. This is something that you've all experienced because at some point, and it usually happens when you're walking along and there's somebody really attractive that you're trying to impress, and you're walking along, it's a little bit dark, and you don't see a hole because you're really you're just so taken by the person you're with that you go and you hit the ground, but you don't hit the ground because you go and you think, oh yeah, I'm just walking along this flat surface. You don't see that there's about an inch decline in that, or half inch, or even smaller. And suddenly, what happens is you collapse down, and you're like, oh my God, what happened? And you look back expecting to see a hole like the size of your whole leg, and it's this little thing like this. And the reason that that happens is because you're ready to hit the ground, and so you contract your muscle. You've increased your active stiffness within the structures, but now you don't hit the ground. And your body goes, huh? And while it says, huh, it relaxes. So then you hit the ground, there's no active stiffness. And the result is that your body begins to collapse because you haven't stiffened your knee, hip, and ankle. And because that's relaxed, the active stiffness within the system is really low, and that's going to cause you to collapse. So when we don't have active stiffness, we're going to collapse. So really what we try and do when we're running, when we're cycling, when we're doing anything, is we're trying to hit maximal stiffness within the joints that we need to be stiff right before we need to contract them. That is one of the reasons that it's hard to increase speed, because increasing top end speed means that the way that we get to our top end speed is we're using our muscles like springs and like struts, and we need to turn them on at exactly the right time in order to store as much energy as possible. And so that's got a neural component, that's got a learning component, and so you get into this process where you get used to the speed at which you want to contract all those muscles in the kind of oriented and complete structure of the movement. And now you turn on active stiffness at a specific time. It's always the same time. So when you go out and you jog, you're always hitting that active stiffness at the same rate. And if you want to go faster, you have to actually hit it faster. And your body isn't tuned to do that really. And so when you try and get up and you try and increase your top end speed, what you have to do is you have to do that by increasing active stiffness, turning the muscle on earlier than your body wants to, so that you can actually go faster. And that's one of the reasons it's hard to improve top end speed. So how real is this? Does this work in humans? This is a paper where they took these controls are students in Scandinavia. These Kenyans are elite Kenyan runners. And basically what they did is they put ultrasound devices on their muscles, and they measured how much their muscles lengthened during jumping exercise, basically like hopping or running. And what you can see is that the Kenyans, these relatively elite athletes, their muscles are contracting just like the turkeys did. They're contracting isometrically. And so you don't see a change in length over the time that they're on the ground. Whereas here, you hit the ground here in the Scandinavian students, and what you're doing is you're doing a shortening contraction, a shortening contraction, a shortening contraction. So basically, if these two individuals were to run against each other, it's like somebody's running uphill, even though they're running on the same surface. One of them is functionally, because they don't have the same economy of movement, these Scandinavian students would be like running up a hill. And so the result is that there's no even comparison in their performance, because this individual is going from here at contact all the way down to here at toe off. And so now you've got this 5 millimeter, 7 millimeter change in the length of the muscle. It's a shortening contraction. Here we're going from this point to about this point, and there's virtually no change in the length of the muscle through the whole time that they're on the ground. I think they get off the ground about 110 milliseconds. Okay, so you can see that in 110 milliseconds here, you're going from about 30, from about 35. So you're decreasing by 5 millimeters. Doesn't seem like much, but if you do that hundreds and thousands of times, you do it 180 times a minute, now it's gonna cost you a lot more ATP than it is to go and do it isometrically. All right, so who's the best in the world? Well, this is a great experiment where what they did is they trained 2 red kangaroos. And what they did with the red kangaroos, they trained them to wear a mask, and then they trained them to run on a treadmill. And so this is basically telling us that when we want to run like a kangaroo. Because look at this. This is how much oxygen it takes them to run. So it's their VO2. And so they're going to get up to a speed here that's going to get up to 25 kilometers an hour on the treadmill. That's really moving. None of our human runners, our elite human runners, are at 16. Okay, so that's way down here. You know, we're doing almost twice the speed here, and this is not even close to their maximum speed. So what happens? They go through what's called pentapedal walking. When it's going slowly, what they do is they move their tail forward, they sit on their tail, and then they move their 4 legs forward, and they do that, and they continue to walk. And it's an inefficient thing. So as you increase the speed at which they're walking, doing the pentapedal walk, you can see that their oxygen that they consume goes up. They reach this speed, this oxygen consumption of about 4 milliliters of oxygen per gram per hour. Okay, and then what happens? They start to hop, and they're going to go from about 7 kilometers an hour to 25 kilometers an hour, and there's going to be a linear increase in speed. And look what happens to their VO2. It goes down, if anything, but really, in us, it would go up linearly with the increasing in speed, but in them, it's not going up at all. And the reason, they have huge tendons. The muscle is really far up near the calf. They have these big legs that are designed to actively contract isometrically, and it doesn't matter how fast they're going, because all they're doing is isometric contraction. So it's going to cost the same to do an isometric contraction at 10 kilometers an hour as it does at 20. Even though you're going twice as fast. Actually, it costs less because you're storing more energy at 20 than you did at 10. And so a little bit less. And so as you continue to do this, they've gotten these guys up to about 40 kilometers an hour. And what you'll see in these animals at 40 kilometers an hour is they do not use any more oxygen than they did at 10 kilometers an hour, because everything is stored within this massive Achilles tendon. And that huge long foot, and that's hits the ground on the toe, it's going to go through this storage, energy return, and you're going to there's no change in VO2 because the isometric contraction that the muscle is doing is the same. You just don't even need as much because you've got more momentum. And all you're doing with your muscle is maintaining that momentum using your muscle as a strut. All right. So what I've shown you today is that your muscle can act as a motor, a brake, a strut, or a spring. The economy of contraction means that a strut is better than a spring is better than a brake, and a brake is better than a motor. Okay? It takes more energy to do a motor than it does to do a strut, to have your muscle work as a strut. The greater your passive stiffness, the greater the economy of performance, and the better speed you're going to run. You're going to cycle, you're going to row, anything. The greater your passive stiffness, we already know from the past that that's going to increase your likelihood of injury. So what you want to do is you want to have good passive stiffness within a range, but not higher than your muscle strength. And then you want to be able to do what? You want to be able to use your muscle contraction to increase active stiffness. And that increase in active stiffness is what's going to allow you to store and return energy for free from each step. And that's going to allow you to perform at a higher and higher level. Okay, so when you think of passive stiffness, think of a dancer. A dancer is very, very passively flexible. They can put their feet up over their heads. They can do all of these moves. They can do the splits, but they can also generate a lot of active stiffness. So right when they want to do a jump and they need to jump these huge heights and then do a split in the middle of the air, They're going to be able to do that because they have low passive stiffness and high active stiffness. They use their muscle contraction to time that muscle contraction just so when you hit the ground, you go bam off the ground. Now you can use the passive stiffness, low passive stiffness to do your split in the air, and you're going to come down and you're going to land in a superhero landing and you're going to look incredible. They look incredible when they do these moves, but you're not going to see them out running. They're not going to be at a marathon because they're going to go along and they're going to go up and up and up, and they're going to use their muscles as motors the whole way, and it's going to cost them so much energy because they have very, very low passive stiffness. So they can produce a lot of power by using active stiffness, but if you have to do that again and again and again, that's the economy part, and that's where you lose out. All right?